everyone, welcome back. We just discussed last class about some set of subroutines, interior point subroutine and wall boundary subroutine. The next immediate thing we can go for, I would say, is free boundary subroutine. Free boundary subroutine is related to pressure boundary condition. We already talked about in gas dynamics, we either give velocity direction as a boundary condition or pressure. Okay. In MOC it comes out to be velocity direction is your theta and pressure comes out to be in terms of Mach number. Okay. Those are your boundary conditions. If say I somehow know an already existing point on a boundary, say this is my nozzle wall and I know how to solve this, and suddenly there is free jet going outside, and say I know this point A and I have already calculated from in this side interior point B, and now I want to find a point C on this. That is my goal. I want to find a point C on a pressure boundary of this jet. That is what we want. Okay. And what is given, since it is a pressure boundary, I know my exit pressure, the back pressure there, that is given, and now I just have to go and find these points. How will I find? I already told you the answer in some way. Mach number is decided by the pressure. That says that I already know my P naught in this region. Okay, if I know my stagnation pressure in this region, I am assuming isentropic flow all through, right. So, I am keeping track of my P naught value all through, and if I know my P naught value at this location, then I can now find my Mach number at C is going to be given by Pb by P naught at C, right. That is giving your Mach number, which will in turn give you nu at C. Okay. Once you know nu at C, remaining thing is simple. If I know this, I am going to send a positive characteristic from B towards C. So, I will have theta B minus nu B equal to theta C minus nu C. Positive characteristic, it will be a difference, right. So, and we know this, we know this, we know this, so I can find this now. Theta C can be obtained. Okay. So, the basic starting point will be I have found theta C. In my wall boundary condition, what did we know? We knew theta C, that was given, and we had to find nu C. Here it is the opposite problem. That is the only difference here. Okay. Now, after we have found this, remaining thing is to find the velocity direction then. We know that the jet boundary will be going with some velocity vector value, some direction, and that will be equal to your velocity vector direction. So, I know that at that location theta C is the angle of the velocity vector, that is found already, that is tan of theta C will be my dy by dx at that location. But what I do not know is what is this curve here. If I do not know the curve, I cannot find the BC line intersecting with this curve AC. So, now I have to find the point C as in the location x y of point C. To do that, we again go for similar approximations. I am going to say this is my point A, this is my point C, and there is B here. Of course, we will start using this also as a curve, characteristic is also a curve, and then now I am going to say dy by dx for BC line is going to be tan of theta B plus mu B plus theta C plus mu C whole by 2. Similar to what we did before, nothing different, it is same as positive characteristic for interior point, exactly the same thing. Now, the other line, it will be different from this. Dy by dx for AC, remember that AC is not a characteristic line, it is a streamline. So, it will go only with theta values, it will not go with theta plus mu or theta minus mu. Okay. Because of that, it will be tan of, I will again do the average business, here it is theta A, there it is theta C. So, it is theta A plus theta C by 2, this is all it will be, this is what you will get. Okay. Now, with these two I have formed an approximate line BC and approximate line AC. With that I am calculating the location of point C. We know lines, two lines intersection we can calculate, geometry, simple geometry, I think it is high school even. So, we know how to calculate the exact location xy from here. Okay. Remaining thing is just I believe I will just write it once, yc minus yb by xc minus xb is equal to dy by dx of bc. This is one of the line equations. Similarly, I can replace this b by a, I will get another line equation for AC. These two if I solve for yc together, I will get value of yc and then I will substitute back to get xc. That is what we will do typically. Okay. So, we have another routine now, which is what I call as a pressure boundary point. That is, I am finding a value of as in the x, y, theta and Mach number for a pressure boundary point. Now, that being said, I actually did from wall corner to a pressure boundary. Will it work from here to another point? Yes, it will, because I will go draw that separately. We said that this is some wall, from here we did an interior point, somehow it came, and from here we got this point C. Now, how will I find this point next? Of course, there is one more characteristic going from here, right. These 2 points will give you another interior point here. That interior point can now do exactly the same whatever we did with this analysis, these 3 points together. Now, this will become your new A, this will become your new B, this will become your new C. Okay, the new values A, B and C. Now, I will just take these 2 points as input, I will get this as the output, and that is the way I just keep continuing along this line. And you will notice that if the jet has to turn like this, the vector also turns naturally. The problem just solves by itself, you do not need to worry too much about it. Okay. So, we have given you simple cases. Now, I just want to discuss a little bit before I go back and give you more routines. Say I have a flow and the flow is supposed to be expanding. What do we expect in this case? I am drawing it as if it is a smooth expansion, does not matter what I want to do. I am thinking about some case here. Here Mach number is m1 and eventually it has to turn and become some m2 which is greater than m1. This is what we expect, somewhere up there, right. Now, if I think about what will happen to my Mach angles, Mach angle, this is mu1 and this will be mu2. Will mu2 be higher or lower? It will be lower. This will be my mu2. This is what I will have finally. Why? Mach number is higher, 1 by m sin inverse. So, it is going to become that. Okay. Now, what is happening to my characteristic if we think about it? If I think about the positive characteristics, there might have been a positive characteristic running like this, and here there would have been a positive characteristic running like this, and then it has now turned this way. Okay. What is really happening? I am having these two, if I think about, they were initially same Mach number, so they were same mu1 value here, they were running parallel. Suddenly, because they are experiencing this expansion fan, this whole region, at the end of it, it is coming out with diverging characteristic lines. Okay. Another way of thinking about it in terms of compression, I have, let us say, a compression wall. I have one mu1 here, but here we know that the Mach number decreases because of the compression. So, it will be a higher value. mu 2 will be higher. Now what will happen, these two, they are both left running characteristics. If you look at it far away, they want to meet each other, that is what we will end up with. Okay. In case of compression happening in the flow, the characteristics will want to converge, the same family characteristics. Now they start talking about family of characteristics. If I think about characteristics that are left running, they are called one family, they are all left running characteristic family, and there could be other family which is right running characteristics. Same family characteristics, if they want to meet, if they come together, then there is compression happening in that region. If they diverge, then there is expansion happening in that local region. Okay. But of course I cannot say this when I am thinking about one left running and one right running I am thinking about. If there is a case where right running is turning this way and left running is turning this way, I cannot tell anything about the flow at that point. I need more characteristics to tell what will happen there. All I can tell is the flow is non-uniform, nothing more. If they are same, these are both left running characteristics and they are coming together, then that means there is compression happening here. In here, there is expansion happening here. Okay. And if there is none of those, eventually they will all be parallel, right. If I think about this particular case, if I think about this particular wave, this will be parallel to this wave there. They are all left running waves I am drawing, right. With respect to the flow streamline, they are all left running waves. So I am seeing that these will become parallel eventually to that also, okay, which means there is no more change in Mach number in this region. Same thing will happen here. If I draw one more characteristic here, this will be parallel to this characteristic. I am not drawing it exactly parallel, it should be something like this, and they will all be parallel after this point. And what about before this compression? They will also be parallel to the previous value. This is what will happen. We will come back to what happens when things go wrong, when they cross. We will come back to this particular corner when things go wrong later, but we will just look at expansion first. Now I will give you one more subroutine, expansion fan, corner expansion subroutine. Okay, I will just give it as expansion fan subroutine. Expansion fan, when I say expansion fan, I am going to think about so many Mach waves in one small fan. Ideally, if I have a sharp corner expansion, typically I am given this angle theta, and now we want to say that the wall has turned, I want to solve this problem. The way to solve it, I know the incoming Mach number at that corner and I know the outgoing theta. Of course I know theta and Mach number at this point. Outgoing theta I know, I do not know the Mach number as of now, but that can be found by our simple gas dynamics calculations. I know the m1, I can find m2 based on this theta. Delta theta is equal to delta nu, you can solve that. Now that delta theta equal to delta nu is what you are going to use here anyway. If I draw the first Mach wave, let us say it is like this, the last one will be like this. With respect to this local velocity vector, this will be one angle, here this will be another angle. Of course this angle is more than this angle. This is all we already know. Now the way to solve it, we already told that there are infinite waves sitting inside here. We will just pick a few of them. Typically I pick 10. Okay. If you want more resolution in data, you can pick 100, 200, whatever, depending on your computer power. Okay. Typically I will pick 10, I will draw only 5 lines here. Okay. First one is the incoming thing, last one is the outgoing, and other things are somewhere in the middle. I am picking 5 points, let us say n equal to 5 right now. What I am going to do is, I know my initial Mach number, I know the final Mach number, I know the initial theta, I know the final theta. All I have to do is distribute this whole data inside here. Ideally I do not distribute in Mach number, what I do is this, I know n equal to 5, right. If I have a, I will have to create 5 points with exactly same xy location, that is that corner. Okay. All points have same x comma y, which is given by your wall geometry. I am going to put 5 points exactly one on top of each other, and I am going to process them in a serial order, n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5, in that order only. Okay. Now how will I create those theta values? first theta value is same as your theta 1, okay, and last theta value is your theta end. These two are known. Now what I do is I linearly interpolate inside here, linear interpolation. I just do linear interpolation in between these, okay. So I will typically pick the 25%, 50%, 75%, 100% kind of interpolation in there for 5 n equal to 5 case. This will be happening. Now once I do this, I go back and ask expansion fan what should I do, delta theta equal to delta nu. So nu will come out to be nu 1 plus first one is nu 1, second one is nu 1 plus delta theta 1, nu 1 plus delta theta 2, etc. up to the last one nu end. You can obviously think about this one, right? It is not very difficult. Delta theta here is the delta theta here, and delta theta here will be the delta theta for from here to here. Like that I can keep on going like this. If I make it all uniform, then this will just be delta theta. I do not need to put delta theta 1, delta theta 2, etc. Now once I find these numbers, I can get my Mach number array. This is coming from here, function of nu. I will get a Mach number array based on, for individual nu values I will find individual Mach numbers at each of those points. This is all actually, if I think about expansion fan subroutine, I just had to create 5 points n equal to 5 here. I could have had 100, it is just more laborious work, okay. I have created 5 points and I know x, y location exactly, and I know theta and m. We told you for every point we should know these 4 values, x, y, theta and m, we know all 4. So I have created some set of points here. How will I use this? If I have an expansion corner in my flow and say I have solved like this till now, somehow I got this kind of solution, that is I knew some points already, and from there I got a wall point, from there I got this point, and from this point I got this interior point, from this interior point I got this interior point, these 2 interior points giving this, these 2 interior points giving this, these 2 interior points giving this, these 2 interior points giving this. Like that I can keep on finding, right. And from here I got a wall point. From this interior point and this wall point I can calculate another interior point, I can find this one. From this interior point and this interior point I can find another interior point here. From this and this together I can find one here, this and this together I can find one here. Like that I can keep on going. But say there was a time, I will extend this characteristic also, say I got this kind of situation here. Now of course I will find all these interior points. Now there is a point where my characteristic is coming close to this wall. If I am the programmer, I know that there is a wall corner there, that should be a given, okay. It cannot be solved arbitrarily. You can solve it arbitrarily if you know this as a function alone, then this characteristic will go there and hit slightly ahead of it, then I will use that value and just it will just go up. The next characteristic will go and hit some other wall, right. It will I will draw one more line here so that it is closer. I know all these interior points. If my characteristic comes and hits here, now I am going to say this theta is different from this theta, so this line alone will diverge like this. Now my expansion fan looks like this. Automatically it will be taken care of if I just use wall point, but if I know for sure there is an expansion corner and I want to take care of that corner specially, then I will create a bunch of points here and then send out characteristics from there. For n equal to 5 it is going to look something like this, 5 points. So what I have to do is, when the characteristic from the right running family comes here, each of these points in that sequence n equal to 1 to 5, in that sequence n equal to 1 will interact with this first, giving an interior point, then that interior point will interact with n equal to 2 here to get the next interior point. from there it will interact to get the next interior point, from there it will interact to get the next interior point, from there it will give the last interior point. I will go through this whole sequence. If I draw this in big, this characteristic somehow is coming from somewhere. These two will interact and give me this point, this and this, then this next n equal to 2 point will go and get me one more point here. This point and n equal to 3 point here will go give one more point here. This point and n equal to 4 will give me one more point here. This point and this point, n equal to 5 point here, and this point will give me one more interior point here. Now I have increased number of points in this line alone and not on this line. Okay, that it will automatically take care of itself. We don't need to worry so much about it. What if it is not a sharp corner but it's a smooth corner? I don't need to worry about anything there. If it is a smooth corner, then I will just let this flow evolve by itself. Let this flow like this, you just keep solving for all these conditions, let it evolve by itself. It will automatically turn. Okay. Why? This positive characteristic will have theta plus mu, but theta is decreasing. So automatically your theta plus mu will also decrease, and that will take care of itself. So you will see that the divergence is happening. If you want to be more accurate for a sharp corner, then I will have to do this expansion fan method. Otherwise, I will just go and use my wall point routine, it will just work very nicely. We still have not given you the full algorithm for solving a flow field around any object yet. Okay, but I am just telling you this partial version of it. Okay. Smooth corners, we do not need to write a special code for it. Okay. As of now, we are at a point where we can go and solve some standard problems without any shocks in our flow. If there is a shock, if there is subsonic flow behind the shock, we cannot solve it beyond that point. But if it is staying supersonic, say it is an oblique shock, weak oblique shock, then definitely if the flow is subsonic behind it, I can solve it. Okay. That is still a special case. But that is the only thing we can solve with method of characteristics. If I think about how to solve this problem, let us say I want to solve flow through some random duct. So this wall geometry is given to me. I know the exact wall function. X, Y values of this wall I know exactly. If I know that, we need to start somewhere. We know that we always solve towards downstream, which actually I already talked about it once last class. We need to be given upstream conditions so that we can solve the problem. Okay. We are given the wall conditions, okay, wall boundary. We should also be given the upstream conditions, which let us say somehow I am given these points initially. Say I know some n points initially. If I know these, all I have to do is start using the routines. Most commonly used one is interior point routine, but typically we have to solve in a logical fashion. So I will start from top wall, go all the way to the bottom wall always. If I think about that, the top wall and the immediate next point, I will decrease the number of points so it is easier to see what is happening. Let us say I will have only n equal to 5. Initial number of points on this is n equal to 5. Now, I will first do interior point between 1 and 2, then I will do interior point between 2 and 3, interior point between 3 and 4, interior point between 4 and 5. That we already saw this, we have marched one step forward. From here, from that point, if you notice, the number of points in the next step was lesser. Here there were 5 points, here there are only 4 points. Next point will step will have 5 points again. From there I will send one to the wall point, I will create a wall point, and then interior points here, interior points here, and then another wall point here. So here in this step I have 5 points. So you have to manage your array such that you can store all this nicely. Okay, it is not going to be all equal numbers. You can store, sometimes it will be 5, sometimes it will be 4, sometimes it will be 5, 4, 5, 4, 5, 4, n and n minus 1 always. Okay, if I start with n being on the wall to wall conditions, this is what you will get typically. If this is the situation, now from here I have to keep on going. Easiest way to draw is not going this point by point business, I will just draw it like this. Since I am doing it on the board, I can do this kind of things. When you are solving it in computers, it may not be this simple. I can draw whatever I feel like here. There you have to go and calculate each and everything. Some such thing. If I now have to keep track of this 5 4 5 4, I will draw those lines here. Something like this, you can keep on tracking those. Okay. This is what I call this MOC fabric, characteristic fabric, right? I call it fabric. I do not see any book which calls it a fabric. Okay. It is just, it is like as if weaving of threads this way and this way. Okay. Why do I call it a fabric? It will become more clearer. It is nicer to use fabric as an example, that is why I use this. Okay. This kind of woven net is what you will form finally. Since I am having an expansion here, I have drawn it such that the characteristics are expanding, except for I made one mistake here, this is actually contracting, but ignore that for now. Other characteristics are all looking like they are all expanding always. Okay. I will show you examples of all this next class anyway. Okay. So, this is the way I will solve for flow inside a duct. This is one of the ways of holding the array values, right. I can hold it like 5 points, 4 points, n points, n minus 1 points, n points, n minus 1 points, like that I can store the array. Or there is a better way of doing things, I like the other version, which is I will take another chalk color, I will pick this pink color. Initially when I am given this initial line, what I will do is from here I will fill this whole triangle first. Okay. What do I mean by fill this triangle? I am going to find all the points inside this triangle and on the boundary. I have found all these points already, which means I am not solving the regular way starting from one wall going to the other wall. I am solving it differently now. I am going to start from this point, there is nothing to be done. I will go to the next point, from there I will want to go to the bottom wall. I will start a characteristic from there, I am solving along my right running characteristics, go along the right running characteristic till it meets the wall. That is how I am going to solve it now. From here I will take this interior point, solve this point, from there go for wall point. Next one, interior point, interior point, interior point, wall point. Next one, 1 2 3 4 5 interior points and then wall point. Next one, 7 interior points and wall point. Just solve this whole thing. When I solve this whole thing, now I will finally have 9 points along the last line. Okay, I started with 5, I will end up with 9. Okay, 1 2 3 4 5 6 7 8 9. Okay, you will end up with 2n minus 1, actually it will be 5 plus 4 here, n plus n minus 1, that is what you will end up with. Okay, you will end up with that. After that, if I start solving only along negative characteristics, there is always same number of points, so it is easier to store it in a nice array. Okay. And plotting also becomes easier if you start thinking this way. I will just solve it like this. From here again you can notice that it is 9 points. Why? I am losing the topmost point, I am introducing a new point at the bottom by creating one wall point. Okay. This is the way I will be solving this whole thing. Now there will always be 9 points, 9 points, 9 points, 9 points, 9 points till the end. There is only one small problem. When we come to the end, if my nozzle say ends here, say my nozzle ends here, I will end up with a situation where I would have solved this line. If you notice, there will still be 9 points, 1, 2, 3, 4, 5, 6, 7, 8, 9 points, right. The next characteristic will be this one. Now I am going outside the nozzle on one end, while the other end I do not have any data. Okay. This is the problem with this. Now I need to be given the pressure boundary point, so I can solve this also. I can solve for this outside region also, pressure boundary point. Yes. Okay. So I can solve up to here. I have gone past the nozzle on one side, while the other side I am still stuck somewhere here. I need data in this region. That is the problem with this kind of analysis. Okay. What if I do the opposite? I will pick another color. I can, I do not know, green on green will work very well. I will take yellow here. Okay. So I will pick another color, and I want to solve all positive characteristics, the opposite now. I will ignore the first one because it is already on the top wall. Anything that is not on the top wall, I will send a positive characteristic towards top wall. I can solve it like this. I am slightly offsetting from the white line so that you can see what is happening. Okay. Again, you are seeing that first one 1 point, second one 3, 5, 7, 9. After that, everything else will have again 9, 9, 9, 9 points. And if I go this way, I will go up to there. Then the next one, there is this characteristic coming from there, and then it goes out into pressure boundary point on the other side. Okay. Again, I will have 1, 2, 3, 4, 5, 6, 7. I missed somewhere some characteristics. There should be 9. I missed one characteristic. Yes, I missed a characteristic here. That characteristic should also be there. Okay. Otherwise, it will not work. 1, 2, 3, 4, 5, 6, 7, 8, 9 points. Okay. So I can go all the way up. It will be 9 points, 9 points. The only problem now will be I have gone past the nozzle on that side, and on this side I am still stuck here. I do not know what is happening on the bottom. Depending on what you want to solve, you can choose. There are 3 methods I gave you. One thing is stepping along the initial line just one step at a time, all points used. If I go that way, I will have n points, n minus 1 points, n points, n minus 1 points like that. If I do this, I will solve up to the end. Even here it will be almost uniform at the exit, which is one nice thing. That need not always be the case. There may be situations where you may want data only on one side and not the other side. For example, if I have a nozzle flow, and I am interested in the flow only in this small region in the center, and I want to solve for method of characteristics based method, somehow I started with some initial set of lines, and I am going to solve only top half. It is a symmetric problem, so I will solve only the top half. It is a 2D symmetric problem. So from here I can solve like this. This is my nozzle. I could have solved like this using only positive characteristic family. This is the most expensive way of solving for region in here. Now I know several points inside this region. This is the most expensive way of solving it. Why? I needed to solve all these extra points to solve for this flow field. Instead, if I had used only my negative characteristics, then I would have solved these. And by the time whatever region is interested is crossed, I have not even gone past this region. There may be times when I want to use this method, there may be times when I want to use the other method, because I am interested only in jet boundary, I am not interested in what is happening in the middle, then I will use my left running characteristics. Okay. Depending on what I am interested in, I can choose. If I am doing a analysis of whether my nozzle will be useful for creating a flow field of a particular Mach number in this region of some particular size, then I will use my red lines, the right running characteristics. If I am interested in finding the jet boundary shape for the same nozzle for a given pressure outside, then I will use left running characteristics. Or if I want to know the exit plane pressure variation, then I will use this other method, n, n minus 1, n, n minus 1, like this, advancing the initial line everywhere together. So there are different ways of solving this. So you can write your code in different modes depending on what your objective is, application is. Okay. Typically, if you are just writing flow through a nozzle, I would say go towards axis, that is right running characteristic typically, if you are solving for the top half. Okay. That is one way of looking at this. Now in all this, we needed this initial set of data points. Of course, there will be problems where we will be given the initial flow condition and then we have to solve from there. That is simple, there is no more trouble there, I can just put how many ever points I feel like there. But there will be times when nobody knows what the data is. That is one such case happens in a nozzle throat. Nozzle throat, we know it is somewhere there m equal to 1. Okay. So if I expand just read this region, if I think about just that region, something like this. Now typically if you are looking at the transonic flow around this region, Mach line contours look like this. Something like this. This is how your Mach line contours look like for transonic flow near the throat region. I am assuming it is choking somewhere there. If this is the case, and you know that as the flow goes through this, and I am assuming flow is going towards supersonic, Mach number should be increasing along these lines. Typically m equal to 1 happens here, and this one is m less than 1 and this one is m greater than 1. How do I know this? People have analytically solved this problem already. Okay. I do not remember the exact paper right now reference, I will give you the reference tomorrow. Okay. I searched for it today, but I will get it to you tomorrow. If it is the author's name is Hall, I just do not remember the journal currently. Okay. Author's name is Hall. It is something very old paper, probably it is 1965 or something. Okay. Completely analytical work. What they really did was they imagined one cylinder this way, another cylinder this way, flow in between two cylinders, choked flow in between two cylinders. That is the problem they solved for. They have given analytical expression for velocity, actually they have solved for u and v. Okay. So from there we can get theta and m if we want. Okay. So we have analytical expressions for those. It is not simple, it is they have done some series expansion based mathematical methods to solve for this region. They have solved it, the solutions are published already on the web. We have used this data and created nozzles and they work well. We have used that kind of starting lines and then used MOC to create nozzles, and that nozzle works well. So I will say that data is reasonably close. So we typically do not use the m equal to 1 line, we will typically pick 1.1 or 1.05, and the solution is not very valid for more than m equal to 1.2. It is transonic, the errors will become higher for m more than 1.1. So I typically use 1.05, 1.1 kind of numbers. For that particular condition, I will find this initial line. Okay. If I find the initial line, after that the problem is extremely simple. Somehow from their contours I have created this initial line. After that I will go and follow this initial technique. Now I have given this initial line, from there I can just go and solve for any one of these methods, the white line thing, marching forward on initial line, or going along left characteristic or right characteristic. Any of these methods I could be using, okay, and solve this. this will give you nice contoured nozzles, a nice flow estimation inside a nozzle that whose geometry is already known. Okay. But the main reason why method of characteristics became famous was because of its ability to create nozzle shapes with whatever exit flow conditions we want. Okay. Typically we wanted uniform flow because we want to create supersonic tunnels where the Mach number is exactly the same all through. That is the idea of this. So, we will go and look at how we can make nozzles. Yes.
Because we need a.
Oh, I didn't talk about access point. Okay. Thank you. I'll talk about that also. That is one more subroutine which is not very different from wall subroutine, but it has slipped my mind. Axis, how will I work at the axis? I want to solve only the top half of my problem. So, there is a right running characteristic that is coming to the axis. Let us call this my axis point. By the way, axis could be axisymmetric, that kind of axis, or symmetry line. Maybe we will call it symmetry point. Symmetry is more clear. We are solving only 2D, remember. Only 2D, so it is only symmetry point. Okay. So, I have a point here A, and I come here, I want to find this B. We know at B theta is 0, theta B equal to 0 is known. So, now I can write this right running characteristic. So, it is theta A plus nu A equal to theta B plus nu B. So, now I can find this nu B. Once I know nu B, I know Mach number at that point. Remaining things are similar to wall point, except for this is, I can actually use a wall point routine here exactly if you want, okay, except for wall condition will be y equal to 0 always. That is your symmetry line. Or you can just have another routine, it is not very difficult. We know that y equal to 0 at that point directly. All I have to do is find when will this line come and meet here. Again I will go for dy by dx of AB is given by tan of average of thetas and mu's, okay, and it is a negative characteristic. So, it is theta A minus mu A plus theta B minus mu B whole by 2. Okay. So, it is intersection of this line with y equal to 0 line, that is the other equation. So, all I have to do is go and substitute y c equal to 0 and get x c from here directly, right. This is equal to, oh no c here, a and b. So, it is yb minus ya by xb minus xa, that is your dy by dx ab. Now, we know that yb is equal to 0, we are given these two values. So, I just have to find xb from there direct. Okay. So, yb is 0, okay, xb is known, x and y are calculated, theta b is 0, nu b can be calculated. So, I know the full point, okay. This is the way it solved from there. Okay. I slipped this, I should have included that, and that is the point, that is the subroutine you will have to use at these symmetry points. Every time when this negative characteristic comes and hits the axis, you would use this symmetry point routine here for all those points. Okay. So, now let us go and discuss how to create a nozzle. Let us say somehow the initial points after the throat is given to you. This is my axis, symmetry line whatever that is given to you. Somehow the initial line is given to you as of now. I will use the same 5 points I will in fact use 4 points on my initial line. Okay. Now, let us say m exit is known to me, okay. That is my target Mach number I want to get from this nozzle at the exit, and I want theta exit equal to 0. This is a standard thing we want for supersonic tunnels anyway. So, I want to get such a situation. So, for this special condition, what we have to do is think about this radius here. By the way, upstream radius can be different from downstream radius, okay. But let us say they are the same currently, or just worry about downstream radius right now. I am going to have the wall turning around as if it is from some point just a circle, okay, with the center somewhere there is just a circle with radius r downstream, r d. Now, I will imagine the wall being on that curve for some time. For how long? Up to a point where this angle comes out to be nu exit by 2. Why? We will see it in a minute. Okay. Say if that is nu exit by 2, that is my last point on my wall. Okay. This is, I have created a wall along this where I have so many points on this wall. Okay. Now, of course, I can go and start calculating characteristics from here and go back and everything. That whole set of things can be done from here. This whole thing can be done. But now I am going to say, after this point, I want to do something very different. So, I will, if I consider a characteristic that is right running characteristic that is coming from the last point on this circular wall, when it hits the axis or the symmetry point, I know that it is a negative characteristic. So, theta, let us label this point as A, okay. Theta A plus nu A is equal to, let us label this point B, okay, theta B plus nu B. This is known, okay. Now, we also know that B is a symmetry point, so this is equal to 0, okay. So, my nu B is equal to theta A plus nu A. Now, I said we are starting from parallel to the axis where theta equal to 0 and rotated by nu exit by 2 angle, which means my this theta at this point, since it is an expansion, isentropic expansion around the corner, it is going to be same theta and same nu. I started with m equal to 1, theta equal to 0. M equal to 1 corresponds to nu equal to 0. I started with nu equal to 0, theta equal to 0. Finally, I went with nu equal to nu exit by 2, which means my theta will be theta exit by 2. Actually, theta will be equal to nu exit by 2 also, because delta theta is equal to delta nu. Okay. Because of that, I will finally end up with nu exit by 2 plus nu exit by 2, which is nu exit. So, nu at B is equal to nu exit, which means at B I have already reached Mach number which I want at the exit. Okay. Once I get that Mach number, I do not want any expansion or compression to happen. So, after this I want this characteristic to just go straight, no changes. That is what I ideally want. Okay. Once I think about that, remaining things are easy. After that, every characteristic should be parallel. Then I have achieved whatever I wanted. I have not completed the full fabric yet. I will just leave it like this. They are all parallel lines, exactly same theta, theta equal to 0, and Mach number exactly same from this point on. That is what I get. I achieved my objective. Remaining thing I need to do is, once I have got this expansion up to this point, I do not want any more change from here till here. So, I need to have a parallel line going there such that along this line, finally when I reach there, this wall should reflect back exactly the same parallel line. If I do that, then there is no more change, they are all parallel. Once I get these parallel, there is no more expansion this way, which is what we wanted, or no compression. So, because of that, what I will do is, the last characteristic I get from here, I will just put the same theta value and nu value at this point on that wall point. That is the key idea of method of characteristics, to create a wall point. To start solving it the logical way, I will start from this characteristic, first one that is going outside of A. I will pick this point, I will take that wall point, put this same theta and nu here on that point. I still have to find the xy. The way to think about it, this is my point A, which is already known to me. Now I have a point B. This is different from the other B there. Let us say I will use 1 and 2. Point 1 is already known, point 2 is known now, okay, from some other interior line. I want to create a wall point 3 where my curve will go some other way. This is my new creation, this is my nozzle design. So, how will I create 3? I am going to say theta 2, theta 3 equal to theta 2, nu 3 equal to nu 2 for the last point on this characteristic. Whatever this is, after this the next point is this. At that situation I will do this. Remaining things is just geometry, similar to what we did for pressure boundary point, exactly the same way. I will say that this is streamline direction. So, I will take tan of theta 1 plus tan of theta 3 by 2, tan of theta 1 plus theta 3 by 2 will be my dy by dx this way. This way it will be average of theta plus mu of these 2 points, similar to pressure boundary point. That exact way we will solve. Okay. So, I will get my xy here and I already know theta and nu. So, I have created one point there. We are interested in xy because we are creating the wall. How will I solve the next one? Pick the next characteristic. This is the last point here. I will put this value here. If I call this one as 4, 5 will have theta 5 equal to theta 4 and nu 5 equal to nu 4. I will get to this. This is the way you will create this whole curve. Okay. And once you get this surface, we have solved and we have created a new nozzle which will give me that desired exit conditions, theta e equal to 0 and me exactly that value. How will I make sure that I have done the correct thing? The last characteristic that is going from here is going to have the value of, this is a positive characteristic. So, theta minus nu is equal to theta 0 and nu is nu b minus nu exit will be the value, nu b is here. Okay. I will get theta minus nu equal to constant is equal to minus nu exit. So, when it reaches the final point, at that point we know we want theta equal to 0, I will automatically get nu equal to nu exit there. Okay. So, it is matching. This is the reason why we wanted to expand only up to nu e by 2. Okay. That is the special thing. If you want to go for some other theta e, then you have to choose something else. That I will leave it to you if you want to think about more. That is beyond course subjects, okay. Course curriculum here. Remaining things I will discuss next class. I will also bring some example solutions next time. I will show you how I have solved cases. Okay. Anything else? See you people next class.